Today's lesson's over section 2.4 about continuity. So continuity has three kind of requisites or requirements to be able to say something is continuous for a function. So if you're looking at one value or one spot on the function, for it to be continuous, your function needs to be defined there or exists, so a value there. Your limit from both sides needs to be approaching a value, so the limit must exist. And then your limit and the definition of that function should be equal to one another. So example 1 here, we're going to look at the definition of each at each point and kind of talk about what makes it discontinuous using the continuity definition that we just described. So at A, the limit at A is not the same from the left and from the right, so then it doesn't exist. At letter B, the limit exists, but the value of B is not defined there, so that part doesn't exist, so it's discontinuous. At C, it's defined, and there is a limit, but those two things are not the same. So therefore, you're not able to kind of match them up, so it didn't meet the third one. And then the last one at D, the limit doesn't exist there because you have one approaching infinity, and then from the right side you're approaching negative infinity. So that's just some idea of what discontinuity looks like for our stuff. Now there's different types of discontinuity. You have removable discontinuity, which we've kind of seen already, is that you are able to remove part of the function to reveal the limit of that function. So here you would be approaching -1 or +1 there, sorry, at that function, or of A, whatever that value would be. So that's removable. So you can remove the open circle part to be able to find the limit. Infinite discontinuity means that you have like your values are approaching infinity or negative infinity at that particular point, whether they're both going in the same direction or not. That would be infinite. And then jump discontinuity is when your function is jumping from one spot to the next over time, kind of like this the greatest integer function that I have posed there. That would be jump discontinuity. Okay. Example 2 here wants us to kind of see if your function is continuous or discontinuous, and then if it's discontinuous, what kind is that? So for my function f, I can see that I can factor the denominator out, and so I notice that at 3, it's removable because I can cancel out the x minus 3 factors there. It also has a infinite discontinuity at a -3 because it creates a vertical asymptote, and so one part's going to infinity and the other side is going to negative infinity. Now sometimes it's kind of hard to see. Now also with a piecewise function, it's not necessarily discontinuous. You have to check where the break is and what those values are approaching to make sure. Here on both sides, when we're approaching the value of 1, we're both getting -20. So that means that the limit does exist. We're both at 1. We're both heading to -20 for both sides. It is defined there because one of them it's equal to 1, and they both match. So that must mean it's continuous function. There's some other notes for f and g to be continuous at A and c being a real number. If they are continuous functions, then addition, subtraction, multiplication, a factor, division are all good. They're all continuous with one another. If you have a polynomial function, that's continuous everywhere, even a rational function, same thing. And a lot of other functions are continuous as well at the bottom there. You can also have one-sided continuity if you have that closed value at the ends, like f of a coming from the right, that limit exists, and then those two things are equal to one another, then we can say that it's a continuous at those points. Same thing on the coming from the left. Now there is a difference between being continuous on an open or a close interval. If you are continuous on an open interval, you're not including the endpoints, so it just needs to be in between those endpoints. needs to be continuous, and so it needs to meet those three requirements. But then if it's on a closed circle, it needs to be continuous in between the two values, and it needs to be continuous from the right of A in this particular case, so right from that left endpoint, and it needs to also be continuous from the left on that right endpoint. Now, another thing that we've talked about in pre-calculus is something called the intermediate value theorem. That just means that if you're looking at two different values and you're trying to see if it crosses or there's a value that you exist in between, then that means it needs to be continuous on that side, on a closed interval. So one of the things we always used to do is there a root for that function in between these two x values? So like here we plugged in 1 and 2 and found that it's -1 and 12. And so notice that the change in sign means that you're going from one side to the next, and we know that the equation that we're given is a polynomial, so by definition it is continuous no matter what. And so because of the change in sign there, it has to be, it has to cross the x-axis there to equal 0. So therefore there is a C value when we plug it in that will equal 0 when we're done. Okay, have fun.